We're going to introduce our project on single image super resolution. We'll start with the problem statement, our tasks, followed by the implemented models. And lastly, we'll show the results from the experiments and finally make the conclusion. The problem that we are solving is the single image super resolution, which is the estimation of a high resolution image from its single low resolution counterpart. The low resolution data are typically assumed to be a downsampled, low pass filtered, and noisy version of the high resolution data. Given the non-invertible nature of the low pass filtering and subsampling, the SISR task is a highly ill-posed problem. With deep learning based approaches, our aim is to exploit the implicit redundancies with the goal to retrieve the missing high resolution information given a single low resolution input. For this project, our aim is to improve the baseline performance of the original SRCNN in two aspects by implementing two different architectures. First, we wish to improve the running speed with fast super resolution CNN. The model learns an end-to-end mapping between the original LR and HR images without any pre-processing. And next, our aim was to ease training of very deep architectures, for which we implemented SRResNet, which we replaced the traditional CNN layers with residual blocks. The original SRCNN is a simple three-layer CNN with bicubic interpolated inputs. The fast SRCNN is different from the original model in three aspects. First, we adopted the original low-resolution image as input without any interpolation. A deconvolution layer is introduced at the end of the network to perform upsampling. The long linear mapping steps in SRCNN is replaced by three steps, which performs reduction of feature space by shrinking, followed by a mapping layer, and finally recover of the high resolution image feature space dimension by expanding. The FSRCNN also adopts smaller filter sizes and a deeper network structure. This improvements provides FSRCNN with matching performance, but lower computational cost.
Our next model is SRResNet, which is first introduced as part of the SRGAN architecture. The goal of it is to avoid vanishing gradients in deep CNN architectures. So instead of simply using convolutional layers, SRResNet uses residual blocks and skip connections. And lastly, for Model 3, we explored a model that achieves SOTA on many datasets, which is the Content Adaptive Resampler, or CAR. The entire framework is trained end-to-end in an unsupervised manner, consisting of two stages, where in stage 1, the resampler net generates a downscaled low-resolution image from high-resolution image. And in stage 2, we use any super-resolution model to achieve image upscaling. The paper uses EDSR, which is based on the SRResNet we just introduced, but the difference is that it doesn't have any batch normalization layers. So now moving on to our experiment. We currently evaluate our models on Urban 100, which is the dataset used by the original SRCNN paper. It contains 100 image pairs with a scale factor of 2. We also have a bicubic interpolated version of it. As shown here on the right, our experiments focus on how growing each network deeper affects the model performance and evaluate the models by using PSRN, which evaluates the image restoration quality. So for our baseline model, we first confirmed that directly growing the CNN network does not necessarily boost the model performance, as it might easily overfit or suffer from vanishing gradients. And next, for FSRCNN, our observation is that the model performs better on non-bicubic dataset, as we give the model more context to learn from the original data. And last, for SRResNet, currently we only have the results for training with 16 blocks, but this is already 4 times larger than previous models. And results here also shows the model trained after 1,000 epochs, whereas previous results are trained for 5,000 epochs. But right now we already find it giving a better performance. So to conclude, our experiments right now verify the objectives we made in the introduction, which is that FSRCNN lowers the model complexity by training without the bicubic preprocessing, and SRResNet alleviates the vanishing gradient issues, and now models can be trained on deeper networks for better results.